We ended our last discussion by looking at three different reactions to the Raven's paradox, the paradox developed by Carl Hempel in the process of trying to develop a qualitative notion of confirmation. He wanted to get past the qualitative to move on to other things, culminating in quantitative and comparative notions of confirmation, but he got stuck at stage one. The diagnoses that we looked at are Quine's. Quine's is messy and disturbing. It's disturbing because if you think about logic, logic tells us absolutely nothing about the way the world is. It merely tells us about the structure that governs what any world might be like. So you can't go to logic, and you certainly don't want logic, depending on scientific facts about the world that you're in. Quine's view looks like it makes confirmation theory depend on scientific information about what the world is like. So Nikod's condition holds when you're talking about natural kind predicates, but it's not clear that you get the same natural kind predicates in every possible world, in which case confirmation theory isn't like logic at all. It's not independent of the nature of the world. So that's disturbing. The more important debate here was between Hempel and basically the Bayesians, between people who said confirmation is a two-place relation, that's what's going to be needed for it to be a logical notion, and the Bayesians who said, nope, it's a three-place relation, and if that means it's not logical, so much the worse for logicality for this requirement. That's where we are when Karnap begins his work. Karnap actually began his work in the mid-1920s. He was one of the instrumental people in the founding and development of the Vienna Circle and the position called logical positivism by some, but he preferred the term logical empiricism that dominated the 1930s in philosophy. He was one of the leaders of this group of people, and he knew more about probability theory than any of the people that we've talked about to this point. Notice John Maynard Keynes talked about probability when he talked about a logical and objective notion, but nothing in Hempel's work signals an interest or awareness of the centrality of probability theory for a decent theory of confirmation. He instead wanted to connect the notion of confirmation with various logical requirements. That's what he was after. A.J. Ayer also did not use the language of probability, but instead wanted to define confirmation in terms of logical relations. If you could do that, you'd obviously get a logical and objective notion. But John Maynard Keynes' approach leads us straight to Karnap, and here's the way to think about that. If you're looking for a logical and objective notion of confirmation, and you're thinking about Frege's work in the foundations of mathematics, Frege is famous for thinking the way you fix the foundations of mathematics is you reduce mathematics to logic. Now, if you had succeeded in that project is called logicism. If you had succeeded in that project, then as long as you had a well-defined mathematical theory, you'd have no reason to question whether you had a logical and objective notion. It's because if it's a decent mathematical theory, it will reduce to logic. And logic, we don't have any worries about. Logic is clearly logical and objective. So John Maynard Keynes' idea was, well, let's just go through probability theory. Take probability theory, it's a mathematically well-defined theory, and if it thereby reduces to logic, if Frege's logicism can be defended. Now, it turns out Frege's logicism can't be defended. What you can do is reduce all of mathematics to logic and set theory, but set theory itself is a mathematical theory and not part of logic. But that's okay. If you could get a mathematical theory like probability theory and reduce it to logic and set theory, that would still be sufficient for defending the logical and objective notion in question. So Karnap picks up because he's much more an expert on probability theory than any of the previous thinkers that we've talked about. So the guiding thought for Karnap's contribution is we can get a confirmation relation with all the requisite links to logic by equating confirmation with probabilistic relevance. So first you have to have the theory of probability, and then we're going to characterize this notion of probabilistic relevance. And it's hard to understate how important a development this is. This is a quote from Clark Gleamore in 1980. Almost everyone interested in confirmation theory today believes that confirmation relations ought to be analyzed in terms of probability relations. It was not always so. Probabilistic accounts of confirmation really became dominant only after the publication of Karnap's Logical Foundations of Probability. Just as before Frege, there was only a small and theoretically uninteresting collection of principles of deductive inference. Gleamore here is dumping on Aristotelian logic. But after him, the foundations of a systematic and profound theory of demonstrative reasoning, so with Karnap and inductive reasoning. So the big change occurs in the work of Karnap. We identify confirmation with probabilistic relevance, and then we spend a lot of time learning about probability theory. So let's start with a simple theory. Suppose you just say this: probabilistic relevance has to do with whether we're going to use this symbol or that symbol or the same symbol. So if we use this symbol, we have positive relevance, negative relevance, and neutrality. So the simple positive theory says E incrementally confirms H if and only if the conditional probability of H on E exceeds the unconditional probability. So the idea is, if you started here, that's how confident you were that H is true. By the time you're done, this is a higher number. You've learned E in the process, and you should now be more confident, more certain that H is true. Then we do the inverse symbol for disconfirmation. And probabilistic relevance thus gives us a theory of qualitative confirmation. And with Bayes' theorem, we can extend it to a theory of quantitative confirmation. So it's important to realize here, Bayesians are not the only people who get to use Bayes' theorem. Bayes' theorem is just an innocuous, very simple theorem of the probability calculus. You don't become a Bayesian by embracing it. Everybody has to embrace it. It's a theorem. Okay, so you use Bayes' theorem, and now you can go from the incremental notion of confirmation, which is a qualitative theory, to a quantitative theory. Bayes' theorem lets you do the measuring. So Bayes' theorem, to remind you, Bayes' theorem lets you calculate this number, the probability of H given E, as a function of this number. And notice that's mathematically equivalent by simple algebraic methods to that. You divide the probability of H given E by the probability of H, and that'll be the same thing as the probability of E given H divided by the probability of E. That's the simple version of Bayes' theorem. Why would that be important to confirmation studies? Go back to the entailment tradition. The entailment tradition said, this is a murky notion. This isn't going to be murky. When we think of this as the degree to which E is predicted by H, does your hypothesis predict this experimental or this empirical result? Well, if prediction is entailment, we have a very simple logical notion over here. This logical notion is much simpler and less murky than this notion that we want to use to understand for purposes of doing confirmation theory. So the idea was, if the hypothetico-deductive thing works at all, then we have a very transparent notion of entailment for getting this number, and then that'll help us with this much more complicated notion on the other side of the equation, the probability of H given E. But then we can just calculate that, because we've got, this is a very easy number to come up with. And then all we need are these other two numbers, and then we can turn that into an actual quantitative measure of the degree to which E confirms H. So the left side of the equations above track increase in the probability of H provided by E. The right side tracks the degree to which H predicts E. And you treat the increase in probability in terms of prediction, just as the entailment view said you should do. The only difference is there's no myth here that the degree to which H predicts E is a matter of entailment. It's just we have to know what that degree is. We got to get it from somewhere. So this form encodes the idea that the degree of confirmation can be measured inversely in terms of the degree to which predictions are found to be true. So think of that as the prediction confirmation mirror relation. This is held in common on this simple theory with the defenders of the hypothetico-deductive entailment view, because they said just as well, confirmation is the inverse of prediction, but then they added that prediction is a matter of entailment. So call this last one the evidence prediction duality or the confirmation prediction mirror relationship. The frame for a probabilistic theory of confirmation is thus begun with the inequalities that characterize confirmation and disconfirmation in terms of probabilistic relevance. This is our basic theory of qualitative confirmation. We then add to this theory the evidence prediction duality resulting from a version of Bayes' theorem, giving us the basic structure for a theory of quantitative confirmation. To this frame, we need one more thing. We need to add a measure for calculating the quantity of confirmation generated by some evidence. Since all we have from the evidence prediction duality is that there is a covariance between the probabilities of H given E divided by H and the probabilities of E given H divided by E. What formula on these elements is the right one for securing this covariance? Here are four proposals. Early accounts said the difference measure was the right way to think about the degree of confirmation being presented. So the difference would be just subtract the unconditional probability of H from the conditional probability of H given E. That will tell you what degree of confirmation E is providing to H. It's a very plausible place to start, but it turns out it doesn't handle lots of cases. You might also substitute a different subtraction. Instead of subtracting the unconditional probability of H from the conditional probability of H given E, you might subtract one conditional probability from another. So you might say, well, what we want to know is what's the probability of H given E, and we'll subtract from that the probability of H given not E. That'll tell us how much confirmation is provided by E to H. Notice both of these just give you simple subtraction problems. These early proposals for a measure on degree of confirmation were quickly replaced, and they got replaced. Basically, the history of this is found in the work in statistics that arose in the 1950s and 60s. People like Savage, for example. So here's an alternative view. It's called the log ratio measure. We're going to call the log ratio measure R. So we had D for the difference measure, S for the subtraction method, and we're going to use R for the log ratio measure. That ratio is the logarithmic function on the following fraction, the probability of H given E divided by the probability of H. When you see the fourth proposal, the log likelihood measure, you'll see that there are analogies between the things being used to generate the measure. The difference measure and the log ratio measure say what we're interested in is the probability of H given E and the unconditional probability of H. Now, what they do with those two numbers is quite different, but the simpler one is the subtraction method, given certain problems, statisticians proposed we move to the log likelihood, to the log ratio measure. And then the one that it turns out is the most widely used is the log likelihood measure. Now notice what it does. It's unique among these four in that it says the degree of confirmation between H and E is a function of the inverse probabilities. And that should remind you of something that we saw in Bayes' theorem. The probability of H given E is a function of an inverse probability. So the log likelihood measure looks like somebody looked at Bayes' theorem and came up with a better idea. In either case, you take the log measure on a fraction. For the log ratio measure, the numerator is the probability of H given E. For the log likelihood measure, it's the inverse probability, the probability of E given H. Similarly, the denominators are different. Here we have the unconditional probability for the log ratio measure. For the log likelihood, we take the inverse probability of E given not H. Those are four proposals. The hard thing is at the purely abstract level, which of these looks to be the most plausible? We've just got four different ones. We can call the top two variance measures because they're derived by subtraction, and the bottom two ratio measures because they've got fractions. Recall that exponential and logarithmic functions are interdefinable. This will help you understand the bottom two, the ones that are both ratio measures. Where x equals b to the power of y, that's equivalent to saying y equals the log to subbase b to base b on x. Now, when the log is base 10, you just drop the subscripted base number and simply write log rather than log 10. This is called the common logarithm. So if you see z equals log of x over y, you can replace it with x over y equals 10 to the power of z. That might make it easier for you to process the ratio measures to figure out exactly what the number is that they're talking about. In any case, we're still at an extremely abstract level, so how are you supposed to think about these measures? How do you decide which is better and which is worse? Well, first you look for cases in which they disagree and see which seems right and which seems wrong. The other thing you can do is formulate general principles that any measure ought to satisfy and see if they do. Here's an example. Notice that for a six-sided die, the R measure on 2 and prime is the same as the R measure on 3 or 5 prime. It's the log of 2. So we're interested in, here's the hypothesis, and in both cases we have the same piece of evidence. You threw a six-sided fair die, it came up prime, and you're looking at the hypothesis that it came up at 2, and at the hypothesis it came up a 3 or 5. Now the measure is supposed to tell us the degree to which our evidence confirms one hypothesis over the other, and it says these are the same. That's what the R measure says. Now think about this intuitively. You throw a six-sided die. You can't see it. You ask me, what number came up? And I said, well, I'm not going to tell you the exact number, but I will tell you this, it came up a prime number. Well, what are the prime numbers between 1 and 6, 2, 3, and 5? Calculate the R measure, and it turns out that it came up prime provides just the same degree of confirmation that it came up 2 as that it came up 3 or 5. That suggests a problem for the R measure. Intuitively, you wouldn't think that that's true. It should provide more evidence for the 3 or 5 than for the number 2. Here's how we generate that result for the log 2 being the result of both of these measures. What we're looking for is the probability of H given E over the probability of H. So H is, in the first case, 2, that it came up a 2. In the second case, that it came up 3 or 5. So for the first case, we get a log of 1/3 over 1/6. The probability that it came up a 2 is 1/6. The probability that it came up a 2, given that it's prime, is 1/3. For the second, we get the log of 2/3 over 1/3. So the probability that it came up a 3 or a 5, that's 1/3, because that's 2 over 6. The probability that it came up 3 or 5, given that it's prime, is 2/3, because there's 3 primes, and 3 or 5 is 2 out of the 3. In both cases, that reduces to the log of 2. Does that seem right to you? That is, does the evidence that the toss results in a prime number confirm that 2 was the result of the toss, just as much as it confirms that either 3 or 5 was the result of the toss? If not, as seems the case, we have reason to abandon the log ratio measure. So that's how you go about assessing which of these measures looks to be the most promising. In fact, the way it goes is you start with the difference measure, you find reasons to doubt that it works, you substitute the subtraction measure, find problems there, then somebody says, I have an idea, let's go with the log ratio measure. Then you have trouble with that, and then you go to the log likelihood ratio measure. So that's argument by counterexample. Another one is, what general constraints do we want on the measure of confirmation? Maybe we want symmetry. So suppose we have 2 pieces of information, E and E prime, both of which support H, but where the first supports it more strongly than the second. That would seem to constrain the relation of these pieces of information to not H as well, so that the second should count against not H less strongly than the first. That's the symmetry requirement. We can get this result by endorsing symmetry. For all H and E in our language and any probability function C, C on H and E equals not C on not H and E. So whatever the positive number is for the relation between E and H, we should just be able to replace that with a negative number when we substitute not H for H. This condition rules out R as well. Use our earlier example. R equals log of 2, which equals I'll let you read the numbers, 0.3 in a bit, but R of not 2 in prime equals the log of 2/3 over 5/6, which is the log of 4/5, which equals negative 0.09, blah, blah, blah. Notice that number isn't the negative complement of the 0.301 number. It should be negative 0.301. Here's another general constraint, logicality. And if you're interested in a logical and objective notion of confirmation, it looks like logicality has a nice ring to it. That's what we're after. All entailments, here's the idea, all entailments get the same degree of confirmation, which is higher than anything confirmed but not entailed. I adverted to this earlier in defending the entailment requirement of Hempel. I said, this looks like a really pristine, beautiful requirement. Entailments are the best form of confirmation you can ever get. They max out on the scale, which means they'll all get the same degree, which is higher than anything confirmed but not entailed. This has some bad news for some of the other measures. D violates logicality, for example. Let E be the claim that a die comes up prime. Let H be anything entailed by this evidence that has a high prior probability. For example, that the toss comes up 1 to 5 inclusive. If it comes up prime, it has to come up 1 to 5 inclusive, because 6 isn't prime. Then the difference gives us 1 minus 5/6, which equals 1/6. Now consider H prime, the hypothesis that the toss comes up 3 or 5. notice E doesn't entail that the toss comes up 3 or 5. It makes it likely, but there's always the little number 2 sitting there as a bugaboo to the entailment claim. So H prime is not entailed by E. But the difference measure on H prime and E is 2/3 minus 1/3, which equals 1/3. And notice that's higher than what we had as the difference measure on H and E. So D violates logicality. The key here is that the hypotheses with higher priors limit the difference value. So that claims that aren't entailed but have low priors score higher on the difference measure. Of our 4 measures, only L, the log likelihood ratio measure, satisfies logicality. So what we've done in this lecture is run through the initial early stages of a Carnapian project. We've gotten to the point where we want to identify which measure we want. We saw 4 proposals, but what we really want to do is make some progress on both which of these measures. Maybe it's the log likelihood ratio measure that we're after. But beyond that, the thing we haven't talked about yet, we haven't talked about which probability function. We've just said we're going to identify confirmation in terms of probability theory, but probability theory simply defines an infinite class of functions called the PR functions. To be in this class of PR functions, you have to satisfy the axioms, but there are infinitely many ways to do that. That's not specific enough if you're interested in a logical and objective notion of confirmation. You have to say which probability function is needed. That brings us to stage 3. We've gotten pretty far. We've found some interesting results from the Carnapian project. The big bugaboo that Karnap spent most of his career working on was, which probability function do we want? We will turn to that in our next lecture.